Hello everybody, and welcome to the beginning of section 18.3. This is on page 109 of your workbook. The topic of this section is called gradient vector fields, otherwise known as path-independent fields. And this is a special type of a vector field that's going to allow us to calculate line integrals in a very different and usually easier way. Okay, so just to illustrate this idea, I think the best way is just to start with an example. So let's look at this preliminary example together. Okay, I want to first point out that this is exactly the same problem that you did back on page 101 in your workbook. You can double check that. We're given the same vector field, the same parametric curve, and the same starting and ending point here. Okay, and so they'd like us to start out, okay, by doing part A. And this is kind of an unusual question the first time that you see it. They would like us to try to guess a scalar function, little f, so that the gradient of that scalar function is equal to our vector field. Okay, how do we do that? Well, let's start with the equation that we want, and that is that our vector field is equal to the gradient of f. And we'll try to work our way backwards here. Okay, we already know what our vector field looks like, so the left-hand side of our equation is just 2yi plus 2xj. That was given in the problem. And then we have to remember what the gradient of a function is. Remember that that's just a vector that has partial derivatives as its components. So the gradient of f would just look like fxi plus fyj. So we have an equation that involves two vectors set equal to each other. And so for that to be true, we need the two I components to be equal, which means that 2y has to equal fx, and we need the j components to be equal. Okay, so 2x has to equal fy. So we really get two separate equations. Let's write both of those down. So fx has to equal 2y, and fy has to equal 2x. Okay, so if we take a look at where we're at, what we know are two partial derivatives. We know that the partial derivative of f with respect to x is 2y. How would we go from that statement back to the original function f? Okay, well, to go from a derivative back to the function, we have to integrate. So to get f from fx, we have to integrate with respect to x. Okay, we could make a similar observation over here. If we start with the partial derivative with respect to y of f, to get back to the function, we have to integrate that as well. So f would be the integral of 2x with respect to y. Okay, let's do both of those integrals. Okay, so starting with the one over here on the left, if we integrate 2y with respect to x, we're just going to get 2yx. I'm going to ignore the plus c for a minute here. And over here on the right, if we integrate 2x with respect to y, we're going to get 2xy. Notice that those two functions are the same. And so a reasonable guess for the scalar function f would be that f of xy is just equal to 2xy, the same function that we got twice. But is that answer really correct? Well, let's check it and see. Okay, so the problem asked us to find a scalar function so that our vector field is equal to the gradient of f. Let's take the gradient and just confirm that that's equal to our vector field. So that would be the derivative with respect to x of our function plus the derivative with respect to y of our function. Okay, and if you take those two derivatives, notice that exactly what we want to happen happens. Okay, the derivative of 2xy with respect to x is 2y, and the derivative of 2xy with respect to y is 2x, and that is our vector field. Okay, so we have confirmed that our answer up here is a correct one. Okay, so we're ready for part B, and part B also has kind of an interesting request for us. They would like us to simply do the calculation f of 3, 0 minus f of 1, 4, and notice that that's a little f, okay? And after we do that, they want us to compare to the answer that we got back on page 101. Okay, so let's work through this together. Okay, so f of 3, 0 minus f of 1, 4. To do that calculation, we just need to go back to the function that we calculated up here in part A and substitute numbers in. So starting with 3, 0, if we plug 3 in for x and 0 in for y, we're going to get 2 times 3 times 0. And then f of 1, 4, same deal. We're just going to plug in 1 and 4 for x and y. Okay, and if we do that calculation, 2 times 3 times 0 is 0, and then minus 8. And we get an answer of negative 8. Okay, now if you want, take a look back at example 2 on page 101. What answer did we get for our line integral? Negative 8. This is the same answer that we got there. So what we've done is to calculate the same line integral that you did back in page 101 in an entirely different way than you did it there. Okay, so this is kind of a preview of something that's known as the fundamental theorem of line integrals.